from homework. So if you guys have any homework questions that you want to talk about, we'll do that before we get started on some new stuff. My suspicion is that there will be a fair amount of questions on the solving pieces. Specifically, we didn't do a lot of example of that in class. And there were some tricky pieces in there that we'll probably, that you guys will probably want to talk about. And that's okay, right? Like, that's the point of not having due dates on things the very next class, right? The due date is Sunday, so it gives you time to try something, be like, and come back and ask some questions so you can actually finish it up, a day or two later, which is nice, right? There's a little bit less of a time crunch when it comes to making sure you got stuff figured out. But what do you guys say? Do you guys have some questions? It doesn't have to necessarily even be from homework 3. It could be from older things than that still, if you wanted to talk about that stuff. Joe?
Could you go over number 5 on homework 3, please?
Yeah, absolutely.
Oh, and can I get the lights?
Yeah, for sure. It's definitely way brighter than it's been in a month today, so.
It's actually nice outside.
It does seem to be pretty nice. All right. So number 5, first thing that I know is that this is not a proportion, so I'm going to have to do the clearing fraction technique. I know it's not a proportion because I have 2 things that are being subtracted on one side of the equal sign. Right there is enough for me to identify that it's not a proportion. So I'm going to identify the least common denominator. If I look at all my denominators, well, I have 2 distinct prime terms. I have x and x plus 3. So my least common denominator would just be x times x plus 3.
You always multiply both sides by the least common denominator?
Yes. So when I do that, I'm going to have x times x plus 3 times 5 over x minus x times x plus 3 over 1 times, I'm going to write this as 2 over 1, just so that we don't get confused on what to do with the fraction or whatever. And then I have x times x plus 3 over 1 times 2 over x plus 3. So far, so good?
Yep.
Okay, let's do some reducing. So bada boom, bada bing. So I'm left with 5 times x plus 3 minus 2x times x plus 3 equals 2x. I'm going to distribute and combine like terms. I'm going to do that all in one step, though. Is that okay, Joe? So negative 2x squared minus x plus 15 equals 2x. Okay, yep. And this is a quadratic. To solve a quadratic, it has to be equal to 0, so I'm going to subtract the 2x from both sides. And then I can either try to factor this, which it may or may not be factorable. It's tough to tell because the leading coefficient isn't 1. Or I can use the quadratic formula, which is probably what I would do if it's me in this situation, because to factor this, I'd have to do the long version of factoring. I don't even know for sure by looking at it if it will factor or not right away, so I'm just going to bowl right into the quadratic formula. Is that okay with you guys?
Yep.
Okay. In general, if I'm solving and the leading coefficient isn't 1, I'm probably just going to use the quadratic formula. Unless it's easy for me to tell that it's going to be factorable. So when I do that, I get positive 3 plus or minus 9 plus 120, I think. Let me just double check that on my calculator. I don't want to goof that up. It is early enough in the morning that I don't trust myself. So that's 129 over -4. And 129 can't be simplified anymore, so that's as good as I can really do. And I just boxed that up without even bothering really to go and check it. Hi, thank you. Haley Evans. Looks like you're creating a new tablet or something.
Right now.
It says between classes.
Okay.
You're welcome. Anyways, Joe, I was saying that I didn't bother to really check that because I remembered the denominators were x and x plus 3, and like there's no way I can plug like a crazy square root in there and get a 0 denominator, right? So I just, as soon as I saw that I was not going to come up with an integer answer, it's like, well, I don't have to think too hard about this. This is going to be good.
So basically, you just, like the first step is finding the least common denominator. And then once you're able to come up with that, you just multiply. You do the steps, do the cross.
Yep, cancel everything down
Yeah.
so you don't have any more fractions.
Exactly. And then you kind of just like slowly solve to
And then it's going to be like a chapter, like a hard chapter 4 and easy chapter 5 problem.
Right.
Yeah.
Sounds good. Thank you.
Yeah, or I guess it could be even easier than that. I mean, you could end up with something linear that's like a piece of cake.
Right.
That's not impossible either. Hells!
Do you think about that?
Yeah, sure. Okay. So again, I would start by looking to see if I can factor anything. Clearly, there's nothing here to factor, though, so I'm going to go straight to identifying the least common denominator. So when I do that, I see two distinct prime terms. I see x and x minus 3, so my least common denominator is just going to be x minus 3. Since each one of those denominators occurs at most one time in any fraction. You good with that? Okay. So I'll multiply both of these by that least common denominator. So just like we did before. Does it help when I'm color coding things like this? Okay. I'll try to remember to keep on doing that. I try to do that when I do something like this where it's sometimes hard to keep track of like what's the original problem and what's stuff that you just did new. So I try to do that. If I forget though, you can always remind me and ask me to do that. And surely if you're doing your own work and you want to color code things, that's totes okay. Even if it's pencil and paper, like don't feel like you have to use a pencil. If you, like color coding helps you, right? All right, so let's do some reducing. All right, so what are we left with then? The first fraction I have just 2x. The second fraction I have just x minus 3. And the third fraction I have x times x minus 1. Which is pretty rad, right? We went from something that was pretty terrible looking to something that's quite a bit easier to see. So combining some like terms here and multiplying things through. I'm going to move everything onto one side now, so I'm going to subtract 3x from both sides and then add 3 to both sides. And I chose to put everything on the right-hand side because I want that leading coefficient to be positive if I can. It just makes it easier to factor. Since I saw that I had a leading coefficient of 1, things are easier to factor if it's positive. So I'm just going to look for two things that multiply to give me positive 3 and add to give me negative 4. That would be negative 3 and negative 1. So when I solve that, my answers are 3 and 1. However, I notice that if I plug 3 into this denominator or this denominator, I get a 0, right? Wah, wah. So that one's no good. I'm going to cross that one out. But I have no such problem plugging 1 in, right? No matter what denominator I plug 1 in, I don't get 0. So that is the only answer that I'm going to keep. Denominators. If I get a 0 in a denominator, any denominator, wherever it's at, as many times as it doesn't matter. If it happens just one time in any denominator, we discard the solution. So obviously, if I plug 3 into x minus 3, I'm getting 0. So I discarded the 3. And only the denominators. The numerator does not matter. Is that okay, Hals? Cool. Of course.
Oh, Mr. Bullock?
Yes, sir.
Kind of a dumb question.
That's okay.
Also, can you go over the simplifying from 2x to the 3x minus 3? You know what I'm talking about? Just real quick.
So the 2x comes from x times 2.
Yep.
And then the x minus 3 is just the x minus 3 times 1.
Oh, so you're just dropping everything down.
Yep, so I just rewrote it down on the next line.
Sounds good. Thanks.
Yeah, no problem. Again, like, I'm trying to show enough work to where you can follow what I'm doing, and it doesn't take a million years to write it all down. If it's ever at any point confusing and you can't follow the work, asking about it is totally fine. And I can surely highlight and explain kind of what's going on and how I went from one step to the next. Hals, what's up?
So on the problem where 1 and 2 like you're right at,
Yeah,
I would like to go over to the
sure. We can do that. Yup. So this is just an adding problem. So the first thing I'd want to do is try to factor, but there's nothing to factor here, right? So since there's nothing to factor, I'll go straight to building my least common denominator. And I see that I have 3 distinct prime pieces. So my least common denominator is just going to be the product of those 3 distinct prime pieces. Which just makes this problem kind of a yucky McYuckerson. But that's fine, we can deal with yucky. So if I look at the first fraction, the pieces that I'm missing is the x and the 3x minus 1. You see that? So I'm going to multiply the top and bottom of that by x times 3x minus 1. If I look at the second fraction, I'm missing the x minus 4 and the 3x minus 1. So I'll multiply the top and bottom of that fraction by those. And then if I look at the third fraction, I notice I'm missing the x and the x minus 4. Hals, is that okay so far? Now, can I reduce at this step? No. Why not? See the addition signs that are outside of parentheses? Yeah. That's why. Okay? So what should I do? I have to multiply all this garbage out and then combine like terms. And then I can check to see if I can factor and reduce. But I have to multiply it all out and combine it together first, okay? So I'm just going to FOIL these things out to start with. So x plus 2 minus 1. I'm just going to kind of do that in my head if that's okay with you. is minus 12, minus 1 is minus 13. And this one I'm just going to distribute through. And then I'm going to distribute through again here. So now everything's all multiplied out. It took a minute, but it wasn't that bad. It was a lot of writing, I admit. But to do the multiplication wasn't really that big of a deal, right? We're just foiling and distributing, which is, pretty manageable. So now I'm going to start combining like terms. So I have the x cubes. And then I have the x squareds. Then I have the x's. And then I have the constant over there. Hal, so far so good? So the last thing I would want to do is to check to see if I can factor that numerator to see if I can reduce it all. Since it has 4 terms, we'd have to try to factor by grouping, right? But if I make 2 groups here for the 8x cubed minus 10x squared, I'd have to take out a 2x squared, which would leave me 4x minus 5. Over here, I'd have to take out like a negative 4, which would leave me 7x minus 2. And the stuff that I'm left with isn't the same in each one. So I can't reduce this at all to do anything more, so I'm just going to be done at this step. Hand wave the fact that I couldn't reduce this at all, mostly because it was, you should be able to tell by looking at it after you've done enough factor by groupings to go, yeah, that one's not going to work. Should be relatively easy to see that the first 2 terms aren't a multiple of the second 2 terms, right? So just the fact that the 8x cubed and the 28x, one of them has a factor of 7 in it and the other doesn't, should be already setting off some alarm bells that that's probably not going to work. You know what I mean? Does that feel okay, Hal? So you see that these adding and subtracting problems actually end up being quite a bit more work more often than not than these solving problems have been. And the reason that is because the technique we're using to do the solving doesn't ever require us to add fractions, which is nice, right? It's the adding fractions piece that's usually really time consuming. Which is why that clearing fractions technique is the one that I really kind of emphasize and I use almost exclusively because it allows me to avoid having to really ever do that, which is nice, right? But you can't do it on these problems that aren't solving problems, right? That's only clearing fractions is only for solving. Megs. Sure. Where are we at here? Okay. This is a proportion, right? So we can do this by cross multiplying. So I'm not going to bother to factor anything at the start because I have a proportion. If you did factor this and you wanted to clear fractions, that's okay to do here also. It would be really no more difficult than cross multiplying. But I would not suggest factoring and cross multiplying because you're just going to end up having to multiply back out what you factored to do after you've cross multiplied. So it's like either do one or the other, but you don't need to kind of do pieces of both. So if I cross multiply, I get this times this and that times that. So I'll distribute things through now. Oops, that needs a squared on it. All right. So next up, I'm going to get everything onto one side. So I'm going to subtract 9x squared. It's going to make 27x squared. And I'm going to add 27. And now I'm going to try to factor 3x squared minus 27x squared plus 54x. The nice part there is that I see that there's a greatest common factor. Oops, that's 3x cubed, excuse me. Just miscopied it. Greatest common factor of 3x with x squared minus 9x plus 18. And the two things that multiply to give me 18 and add to give me negative 9 are. So this is going to spit out three solutions. X is 0. The x minus 6 gives me x is 6. Gives me that x is 3. But I still need to check to see if these are going to give me a 0 denominator anywhere. So I notice that if I plug x equals 0 into x squared minus 3x, I get 0 minus 0. So I should discard the 0. And if I plug 3 into x squared minus 3x, I get 9 minus 9. That's 0 also, so I should discard that one. But the 6 is okay. No matter which one I plug that into, that's going to work out. Is that okay, Megan? Okay. Just FYI, if you plug 3 into the first denominator, that also gives you 0. So, right? 9 minus 18 plus 9, yeah, that's 0 also. So this one had two extraneous solutions. But that's okay. You guys feel okay on this? Or at least a little better anyways? The general idea here is just turning it into some kind of polynomial and then solving the polynomial using our existing strategies is basically what we're doing here. So we're just applying the same techniques we'd used in chapters 4 and 5 to do most of our solving once we got the polynomial equation out of it. Okay, so let's go ahead and start the new stuff for today. This should be, I think in general, students find this topic easier than the previous things we've been working on, which is nice, right? So this is a graphing topic. So we're going to be talking about simple rational functions and how to graph them. I abbreviate that as SRF because, well, that's a lot of letters, and I'm going to write it a bunch of times probably today, and it just, like, why make your life harder, right? Just come up with some abbreviations. Whoa! And that's better for everybody. So let's start by defining what we mean by a simple rational function. So a simple rational function can just be written as a degree 1 or less polynomial over a degree 1 polynomial. So typically we'd write that simple rational function in one of two ways. It'll either look like y equals a over x minus h plus k, or y equals ax plus b over cx plus d. So those are the two typical ways that a simple rational function would be written. So there are a couple of key features that we need to be aware of when we're graphing a simple rational function that we need to make sure are included. The first key feature is called the vertical asymptote. I just abbreviate that as VA. Again, a lot of letters. We use that a lot. Yes, sir. Oh, you're just doing something. I thought that was a hand. You were just stretching or something. So a vertical asymptote is just a vertical line that the graph approaches but does not cross. Okay, that's far enough. And so just again, remember, vertical is up and down, straight up and down. A horizontal asymptote is the other key feature. I'm going to abbreviate that as HA. Again, we use that a lot. Is a horizontal line the graph approaches but does not cross. So the way that we're going to graph these things is as follows. First thing we're going to do is find the vertical and horizontal asymptotes. So if it's in the form y equals a or a over x minus h plus k, the vertical asymptote is just the equation x equals h, and the horizontal asymptote is the equation y equals k. If we have the other form, the vertical asymptote is x equals negative d over c, and the horizontal asymptote is y equals a over c. So far, so good. Okay. After we've found those asymptotes, we're going to graph them. Oops. Then we're going to find 3 points on each side of the vertical asymptote. And then we're going to plot those points and draw the graph.
Is this a challenging process?
I think that in my experience, students do not have too hard of a time with this, especially in comparison to the things that we've been doing.
Yeah.
Typically, students do quite well with this. Okay. So let's do a couple of examples. So let's say we want to graph y equals 2 over x plus 3 minus 1. So the first thing I'm going to do is identify the vertical and horizontal asymptotes. Now, how do I know which formulas to use? Well, I'm just going to look at the form that my problem is in. This looks like that first form that we had listed, right? So the formula says that the vertical asymptote is x equals h. In this case, what is h?
3.
Very close. It's negative 3. Remember, the general form has x minus h, so the h is going to be the opposite sign of whatever it appears in the problem. Right? We've run into that a couple of times, right? When we were looking for the vertex for absolute value functions or quadratic functions, that had happened to us before. The horizontal asymptote is y equals k. The k in this situation is negative 1. So the k has a plus k in the formula, so the value of k is just what it appears in the equation.
Regardless, even if it's a positive, or never mind.
Yep, doesn't matter the sign, you just take the sign with it, whatever's in front of it. The h is the opposite sign of whatever's in front of it. That typically is the trickiest, or the thing that students make the biggest mistake on, is goofing up the sign for h. Okay, so we've done that. So I'm going to make an xy table. So I say I need 3 points, and then I need to have the vertical asymptote, and then 3 more points. So the vertical asymptote doesn't have a y-coordinate with it. Notice that if I plug negative 3 into my function, my denominator is going to be 0, which is undefined, right? So I'm just gonna like color in the box underneath my vertical asymptote to remind myself that there's no point there. And now I'm free to pick my x's, just as long as 3 of the x's are less than -3 and 3 of the x's are bigger than -3. I'm just going to pick the obvious ones. Right? No need to make this complicated. Pick numbers that are easy to deal with, that are relatively close to that vertical asymptote. Typically, the closer you pick your points to your vertical asymptote, the better off you're going to be. Now, how do you find the y-coordinates once we've picked the x's? You just plug them into the function, right? So -4 plus 3 is -1. 2 divided by -1 is -2. And -2 minus 1 is -3. You could also do this on your calculator if you don't trust your arithmetic. Since there's a fraction, I'm going to use that fraction command. So I'm going to press alpha and y equals and choose the first option. And then I can just type it into my calculator. Boom. Everybody cool with that? Now I'm going to just fill in the rest of these using arithmetic because I trust my arithmetic. So that's going to be -2, and that's going to be -1 2/3, and that one is going to be 1, and then that's going to be 0, and that's going to be -1/3. So now I'm going to draw my graph. 1, 2, 3, 4, 5, 6. 1, 2, 3, 1. I'm going to start by drawing in my asymptotes. So -3 is my vertical asymptote. So I'm going to count on the y-axis to -3 and draw my vertical line. And my horizontal asymptote is -1, so I'm going to go to the y-axis, find -1, and then draw my horizontal line. Everybody okay with how we draw those asymptotes? It's pretty easy because they're just vertical and horizontal, so you just need to find the right spot on the correct axis and then draw your line. I draw them dashed because they're not actually part of the graph, so you should draw them as dashed lines like that. Now I'm going to plot my points. So -4, -3 is here. -5, -2 is there. And -6, -1.6 is there. And now to draw my graph, I'm going to follow my asymptote, go through my points, and then follow my other asymptote, just as I move from left to right. Because remember, your graph cannot cross your asymptotes. And then I'll graph my other 3 points, so -2, -1, 0, and 0, -0.3. And then again, I'm going to start next to my asymptote, go points, and then follow my asymptote. And that's what my graph should look like. Notice that the part of my graph that follows the horizontal asymptote is horizontal. And the part following my vertical asymptote is vertical. Right? Just to help give you some, remember how to kind of draw those graphs. So the 6 points that we plotted should never be all connected, right? 3 of them should be connected, and then you should have to pick up your pencil to draw the other 3. Cool? Joe?
May I use the restroom, please?
Absolutely. And that's it, right? That's no big deal, hopefully, right? That seems fairly easy, I think, especially in comparison to what we've been doing, which required so much more bookkeeping and keeping track of stuff. That's pretty straightforward. Let's do another one with a simple rational function in the other form. Let's do this. So here we have 4x minus 3 over 2x minus 5. So the vertical asymptote here is negative d over c. So here's my d, and here's my c. So I have negative of negative 5 over 2, which is just 2.5. And my horizontal asymptote is y equals a over c, which is just 2. Everybody okay there? Great. So again, we'll make our XY table. So I need 3 points, and then my vertical asymptote, which in this case is 2.5, and then 3 more points. So I'm going to pick 3 values less than 2.5. So I'm going to pick 2, 1, and 0, and then 3 points bigger than 2.5. So I'm going to do 3, 4, and 5. Again, no reason not to be, to pick decimals or any, just pick whole numbers. It doesn't really matter. Okay. To get the corresponding y coordinates, I'm just going to plug in the value for x and into my original function up here and evaluate. So if I plug 0 in, I get negative 3 over negative 5, which is 0.6. If I plug 1 in, I get 4 minus 3 over 2 minus 5, which is negative 1/3. If I plug 2 in, I get 8 minus 3 over 4 minus 5. So that is going to be 5. Oh, negative 5? It's like, that's 5 isn't right. So 5 over negative 1. So that's negative 5. If I plug 3 in, I get 12 minus 3 over 6 minus 5, which is 9. And we have 16 minus 3 over 8 minus 5. So 13 over 3, which is like 5 1/3. And we have 20 minus 3 over 10 minus 5, which is 17/5, which is like 3 2/3. And again, since we're graphing this, like a decimal is fine. Rounded to 1 decimal place is probably sufficient, right? Yes? I'm just plugging, like, I put, for example, I'm just taking 0 and plugging it into both spots. So 4 times 0 is 0, and 0 minus 3 is negative 3 on top, and then 2 times 0 is 0, and 0 minus 5 is negative 5, so I'm left with negative 3 over negative 5, which is just 0.6. You're welcome. And again, you can do that all in your calculator. I'm doing it in my head because, frankly, it's faster for me and feels less annoying than trying to push the buttons out with my mouse on the calculator. If it was just my calculator in front of me, I probably would be less annoyed by pushing the buttons on my calculator, but the calculator and the mouse is so slow to me, it just drives me crazy. But certainly use your calculator if you don't feel good about your mental math skills and like converting fractions and holding all the numbers in there. Like, that's not a trivial task for most of us. I've just been doing this for like 30 years, so I'm pretty good at doing stuff like that. But like, that's not the expectation that you're at that same level. If you need to use your calculator to do that, do it. No big deal. Cool? Everybody good? Gals? Absolutely. Yep. All right, so let's finish up this problem here. Let's see, 0, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5. So 2.5 is my vertical asymptote. Let's start by drawing that in first. And then positive 2 is my horizontal. So I'll put that one in next. And then I can start plotting my points. So I have 0 and 0.6, 1 and negative 0.3, and then 2 and negative 5. So there's one arm. Then I have 3 and 9, 4 and 5.3. And then 5 and 3.6. So I'll draw the other arm. And there's that. Is that okay, guys? Yo, Alexis?
So, I know you, like, yeah, and I know you think like that.
Mm-hmm. That's the horizontal asymptote. Yeah, no problem. Again, like, more often than not, the explanation is easy, but if you're not sure as to why I did something, like, speak up, you know. You're not going to learn by not saying anything, right? So if you have the question, I'm sure somebody else has the question too, so no big deal. Again, happy to repeat myself or to do it again or explain some more or, you know, re-emphasize something or show some more detail or whatever we might need. No big deal. In fact, it just shows me that you're paying attention, trying to understand what we're doing, which is good, right? Like, that's what we're hoping for. So generating the graphs, like, not too big of a deal, right? Especially compared to some of the things that we've been doing recently, this is considerably easier, I think, right? The last topic here that I want to talk about is domain and range. Simple rational functions again. And if we remember, domain and range can be pretty difficult at times. Fortunately, this is not one of those times. So it's easy because there's one rule for all simple rational functions. The domain is going to be all real numbers except for whatever the vertical asymptote is. And the range will be all real numbers except for whatever the horizontal asymptote is. Which is lovely because those two things were not very difficult to find. So if I go back to the previous example that we were just working on, the domain would be all real numbers, in our case 2.5, because that's where the vertical asymptote was. And the range would be all real numbers except for 2, which was where the horizontal asymptote was. So this is really easy also, right? You don't really need any new information that we didn't need to generate the graph to do the domain and range. And remember again what the domain and range is talking about are all the domain is the x coordinates that are used in your graph, and the range is the y coordinates in your graph. So what this is saying is you can pick any x coordinate other than 2.5, and there's a point on your graph that has that x value somewhere. So like if you'd picked like -3, well, there's certainly a point there that corresponds to an x coordinate with -3 on it, right? And you can do that for any x coordinate except for where the vertical asymptote is, because the graph doesn't cross that point, so there's no point on the graph that takes that x value. And then the range is the same thing, except we're talking about y coordinates. If we go back to the first example, domain in this case is all real numbers except for -3, because that was where the vertical asymptote was. And the range was all real numbers except for -1, because that's where the horizontal asymptote was. And that's it for this lesson. So I want to just say for a moment, graphing rational functions in general is quite difficult. That's not something we're going to do in this course, though. We're only going to worry about these simple rational functions where things behave quite nicely. If we don't restrict the degrees of the numerator and denominator as we did in our definition, things can get very strange very quickly, and that's beyond the scope of this course.